and how to do such a hypothesis test for a single variance in a specific example. So let's just shortly recap the story. We are producing tablets in a medical company. The target is 1 milligram per gram, and the variance, of course, should be as small as possible. Now, here is the data as we have seen it. Actually, not the data. So far, it's just the claim. I'm sorry. Now, the company claims to the authorities that are controlling the company that the variance is not more than 0.05. The true variance is 0.05 squared. Now, what is the relevant null and alternative? In case, let me see. Actually, it's a bit maybe difficult to know, but nevertheless, let's do the null. That's at least the easy part, because I think that's basically, what is put to us in the specification of our task here. The alternative, well, again, of course, we need to think here. Does it make sense? Is it sensible to prove one or the other? Actually, we are not really told until on the next slide we are told what I would like us to do. But the relevant situation is here, if you were an authority that would go check, you would want to see if you could prove that the variance is actually larger than the company is stating. Actually, I mean, this is where some may sit and say, why not the other way around? And yes, it could be the other way around. It actually would depend on who is doing the study in a way. You could ask the company to prove that they are within a certain, let the company prove that they are close to the specified variance, or even within some specification limit. That is another type of hypothesis testing where you want to prove that something is small, or when you want to prove that nothing is there. That's in a way the opposite proof as what we are throughout in this book and this course is using, and what people in 99% of the time out there globally, when they do testing and investigations, they use this way of thinking. I just want to raise it here because if you sit and think, why not the other way around? You are a good thinker. That's just why I want to reassure you. It's not because your brain there's something wrong with your brain. And as I've told you earlier, I can completely, I live with that and accept the fact that our brains are limited. But it's good thinking. Why not prove the other way around? Yes, that could be done. You call that equivalence testing. You call it claims testing. There are different words for that. So you can change the roles of null and alternative. But again, you can leave it out of your brain for this course, because we're not jumping into this sort of changing the roles of the null and the alternative in this course. But it does exist, right? It's good to know that makes sense to think like that. If you want to prove that something is small, you should actually change the way you think, and it can be done. Anyway, it's closely linked to the confidence interval then, and you should focus on the confidence interval. Here we do this test because that is what we are actually asked to do. This is when people from the outside would go and sort of check the company, and if the only interesting thing for the outside people would be to prove that the variance is larger, that would be the interesting case where they have a case to move on with. So here's the data, the same data as before. 20 tablets, mean, small x bar equal 1.01, standard deviation of 0.07. Carry out the hypothesis test. What was, it was n minus 1 times s squared, like this. 19 times 0.07 squared divided by the claimed variance, right? So we measure, in a way, you can see this is a measure of how much larger is the observed variance compared to the claimed variance. I would say that makes sense to compute this number somehow. It expresses How bad is it really? What is the number? Where did it go? Here it is. On this scale, it's 37.24 or larger. At least when I've rescaled it with 19 as the formula asks me to do. How should I evaluate 37.24? Right? I'm having some measure of how bad is it. The measure is 37.24. How the heck could I evaluate whether this is a severe difference or not a severe difference, given the situation, given the randomness, the variability in the system? This is again where the distribution theory comes in, and if we use this chi-square 19 distribution, we can evaluate whether 37.24 is really severe, or severely large or not. Because we could find a p-value. We could take the chi-square 19, we could take the number 37.24, and then we could find out, here's the p-value now. Now I do it the p-value way, not the critical value way, I do it the p-value way. I try to find the p-value. The p-value is the probability that some chi-square distribution actually is larger than or equal to the observed, because it's a one-sided hypothesis test we are doing. Should we see if we can find that p-value? Let's find it in or try to find it here, if we can. Here's the limitation of the table. Let's look at the 19 here. What was the observed chi-square was 37 point something, right? So I can see that I'm here, right? I'm in between the 1% and the 0.5% point. I'm in between the 1% and the 0.5% point. So actually I'm maybe okay. I cannot actually complete this one with an equal sign. I could say that the p-value is less than 1% from looking at the table. This is alone due to the fact that the table only has limited information. I can actually find the p-value. Not that it's extremely important to be exact on the p-value itself, so the table could suffice here. I could find the p-value by looking at p chi-square taken in, what was the number, 37.24, with how many degrees of freedom? With 19. Now p chi-square gives us the probability of being to the left of this number. We want the probability of being to the right of 37, to be further out than 37. So I say 1 minus this. The probability is 0.007. Which of course then is, it's right in the middle between 0.005 and 0.01. What is the conclusion? What is alpha? Did we discuss this? We should have decided this before starting to look at the numbers. Actually, I forgot to say that. Why not use the 5% as we usually do? If we use the 5%, what do we do here? What's the conclusion? Do we reject? Have we proven that the variance is much too large? Is the variance unlikely large? Yes, it's very unlikely. It's a very small probability. It's below alpha. So, since the variance has become unlikely large, we have proven. Can you prove that the variance is larger than this? If I should make a short answer to the question, Yes, I did prove that. At least up to the type 1 error I'm using, but if we agreed on that, I proved it. That was hypothesis test for one variance. Let's finish this example with a little addition before we move on to the final part. So we continue here, Georgi, with this part. Just to refresh our minds that actually this production thing was a part of two things. It was part of the mean, and it was partly the mean, and it is partly the variability of the production. Both things are important. And we could think about, now we have found two things regarding the variance. We have found that we can prove that it's larger than 0.05 squared. If I jump back to my confidence interval from before, here it was. I had a confidence interval on the standard deviation somewhere between a little larger than 0.05, which fits with our rejection, right? A confidence interval a little larger than 0.05, even though there is a one-sided, two-sided sort of abstraction on top of everything else here. We don't have to dig into that. So the variance seems to be a problem here. If it's important that the standard deviation is 0.05, we see now, I jump back to my example. What about the target? Could I prove that we are off target? Well, then I'm back in what I taught you a few weeks ago, and which I repeated today. We could do a t-test on this. We could compare the 1 minus the observed and taking 0.07 over root n. This is the t-test for one sample situation. What was root n? That is root 20. What is this? Well, I prepared this here in R. The t-test statistic is 0.62. If I plug in this in, just not to confuse you, I can say minus 0.6227 if I take it like this. What is the p-value then? It's good with some options. I forgot to put the degrees of freedom, it tells me, so let me put 19 and try again. The p-value becomes the probability of being to the left of this minus 0.6 and twice, because I'm doing a two-sided confidence interval. So the p-value here becomes, here I have minus 0.62, and I would somewhere here have plus 0.62, and the p-value is this together with this, which was 0.54. Can I prove that the mean of the production is off target? Can I prove that I'm off target? What would you say? What have I found now? Do I have an unlikely off-target situation, or do I have a likely sort of little small deviation from the target situation? That's how you should look at this probability. I mean, the probability here is the answer. And we have, just to be easy on you, if a probability becomes below 5%, we say it's small. If it's not below 5%, we say it's not small. That's the best way of saying it. And it expresses the likeliness of the data, given that the hypothesis is true. So am I in an unlikely situation here, assuming that I'm on target? Assuming that I'm on target, I would say no, it's not unlikely, because the probability is not small. It's not unlikely. So I'm in a likely deviation situation. So the null hypothesis has not been proven wrong. I'm not far away from the null. I'm close to the null. So when I'm close to the null, can you prove that? Then the answer is no. I have to accept the null, or at least less severely expressed, but meaning the same thing. I cannot reject the null, underforstået, to be understood. So, question, sorry. Why square root 20 and not square root 19? Well, that's because that's how the formula for the t-test statistic looks like that. The 19 is for the degrees of freedom, but if I rapidly jump back to table, you can see that when we use in the test statistic, it's root n. So that's how it works. Okay, so for this production, it seems that it's the variability which is the problem and not the target situation, right? It's just to be clear on us that both things are in focus and should be in focus. The target, the means, and the variability. And we have the tools for that now. However, we have to jump on, so we move on.